balancing. And I think the first thing you have to look at is what we're trying to achieve, which is ultimately that a user can connect to some sort of service, and that service is able to be balanced up between a bunch of servers. So we're not overwhelming one server with hundreds of gigabits of requests. So firstly, and I'm not going to spend a whole lot of time on this, we're actually pushing as much as we can into the application. So what does this mean? It means that ultimately, to achieve this goal, we don't need to have every request hitting a single VIP. Application-based load balancing is the idea that we hand out a unicast IP address per server that we want users to hit. So we'll say to, say, 1/500th of users that they are to hit this server over here, and another 500th that they're to hit this server over here. And when we're in a position like Twitter are to actually control the application that most of our traffic is originated from, we're in a good position to do this. So wherever we can, we've first started by pushing all of this problem up to the application and taking it off the network layer. Obviously though, if we're giving out a DNS response for www.twitter.com, we're not always able to do this. You know, well, if someone's using the Twitter app, this works well. If they're just hitting our web address, we actually need a VIP that's able to respond to them. So in this, we've spent a lot of time figuring out how to virtualize this functionality off the load balancers, and how we would achieve equivalent or better functionality than we are today. So firstly, we need to actually look at what the load balancer does. And it does a reasonable number of tasks, and some are harder than others to virtualize. So the first thing the load balancer does is it distributes traffic over a pool of servers. So in this case, we might have, say, 60 servers in our POP in Frankfurt, and we're distributing traffic evenly over all of them. We're gracefully inserting and removing hosts, and what this means is that when we take one host in or out of service, we ensure that the same clients are hitting all of the other hosts. So one host bouncing shouldn't cause every TCP session to move between servers, because if this happens, every time we push an update to a server, we're going to disrupt all of our users in that POP. The load balancers perform health checks, which I'm sure you're all familiar with, in that they'll go and hit the server and do a HTTP request. They'll check that it gives an HTTP response. They'll do other health checks as configured, but we're limited by what the load balancer vendor wants to expose to us. And historically, we've found that getting features exposed that we want has been very difficult because we have to compete with other customers of these load balancer vendors. They'll also advertise routes into your network, and they'll map traffic to hosts that aren't necessarily directly connected. So we may have a load balancer that is on the edge of a data center and a server buried deep within the data center, and we need to map traffic to a specific server. So this will generally involve some form of tunneling technique, such as GRE or some destination NAT. And we get some sort of flexible load balancing methodology. And what I mean by this is that if we use a router-based hash, we're actually going to create a hash based on layer 3 and 4 information and assume we have enough randomization in our requests to map traffic roughly evenly between servers. Whereas on a vendor load balancer, we're doing layer 7 inspection, and we can start counting the number of TCP sessions to each server and balancing them out. We also, in this light, have the ability to gracefully migrate sessions, and that we can take a server out of the active rotation to be given new sessions, but leave all the old sessions there until they time out. So we kind of sat down and worked out, well, what can we do with these functions? Do we need all of this functionality? And can we actually virtualize this either upwards to the router or downwards to the server? So the first thing we realized is that the load balancing functionality can be pushed into equal cost multipathing on our routers. So for all the router vendors, they can do between 64 and 128 wide hashes, and they're able to use layer 3 and 4 information for this. So they can load balance wider if needed by doing a couple of things. Both are quite nasty tricks. The first is a little bit nicer, which is to do DNS-based load balancing, where we return, instead of one VIP for www.twitter.com, we return, say, 16 VIPs. And then each VIP is load balanced onto a separate set of servers. So we assume that the clients will get different VIPs at random and spread themselves between them. The other option is to do some form of multi-layered ECMP, where we ECMP firstly from a router into a series of routing instances, and we then ECMP onwards onto the servers. This ends up with a significant amount of resource burn on any vendor's router. So, firstly for ECMP, I'm going to do a quick summary of the difference between consistent and non-consistent ECMP. or in other